This week in lab, you will be learning about solutions, the stoichiometry of compounds in solutions, and how to measure the concentration of a solution using a technique called visible absorption spectroscopy. And so a key thing to know in the beginning of discussing visible spectroscopy is that light interacts with matter. And this is something that we may take for granted, but we see objects with color. And these objects have color because of the compounds in them that absorb specific wavelengths of light. And so I included this image here with a lot of different transition metal complexes that absorb a wide range of different colors, and therefore the color that we observe is beautiful, and it's a wide range of different colors that we can see in these different complexes. And so just as a bit of a reminder, of course, we've learned at some point in our education about the visible spectrum of light, and that is within the larger electromagnetic spectrum between infrared and UV wavelengths, and the different colors have different wavelengths associated with them. A smaller wavelength is a higher energy, and a longer wavelength is a lower energy. So that means that of the visible spectrum, the lowest energy would be red, and the highest energy would be more of that deep violet color. All right, so in a visible spectroscopy, we might imagine that these are the wavelengths that we use, and spectroscopy is just a word that has to do with measuring things with light. All right, so before we get into the actual details of how the spectroscopy works, let's talk about solutions. So in the lab, you will pretty much every week be using solutions. And this is because a lot of reactions take place most efficiently when there is a solvent present and so on. Solutions are very convenient for chemistry to occur. But whatever you find in the fume hood, we'll typically call it the stock solution. And the stock solution will have a specific concentration associated with it. Sometimes that is unknown, but usually a stock has a known concentration, and this should have more decimal places associated with it. But just for this illustration, let's say it's a 1 molar stock solution, and this is meant to represent the concentration of 1 molar. It's a pretty high concentration. As you can imagine, we can have solutions with greater concentration or less concentration, and essentially that just means the amount of particles per solvent is greater or less. So particles of ions, particles of molecules, solutions could be made out of a lot of different solutes, but the idea is that the ratio of solute to solvent determines the concentration. We have discussed previously the concept of molarity, but molarity is moles over liters. And so if I take molarity times liters, that gives me moles. So I can use this formula here to relate the concentration and the volume initial and the concentration and volume final for a solution, because the moles of solute present should be constant. If all I'm doing is adding more solvent to dilute something, the amount of solute doesn't change. Now, if I take a small part of that and put it into a test tube, sure, like if we look at the representation I have here, obviously there are fewer moles of solute in this test tube compared to the first test tube. So this is because as more solvent was being added, a small part of that solution was taken out and put into the test tube. because otherwise the test tubes would have overflowed with the amount of solvent present. So these are just samples of the diluted solutions. Okay, hopefully that is not confusing. But essentially, as we move to the right, the ratio of solvent to solute is increasing, or we could say we have a decreasing solute to solvent ratio. Either way would be appropriate. And just to illustrate how we can use the molarity formula and calculate the concentration of a new solution when we dilute it, we could take 1 milliliter of our stock solution and mix it with 9 milliliters of water. That would give us a total volume final of 10 milliliters. But in our initial solution that we removed, that was 1 molar, we only took out, I don't know what happened to my undo button. Oh, here it is. We only took out 1 milliliter, which is equivalent to, if we convert, 0.001 liter. And I'm using the unit of liter, even though technically it doesn't matter if you use milliliters in this dilution formula, but just to be consistent with the molarity formula, having liters for units. All right, so in my final solution, I'm not sure what my concentration will be, so I let that be my X, but I know that my total volume now is going to be 10 milliliters because I'm mixing 1 mil and 9 mil. So my final volume should be 0.010 liters. And so if I solve for X, I would find that my concentration is now 0.1 molar. Basically, this is a 1 to 10 dilution, so my concentration should go down by a decimal place. We could continue this, so let's just imagine that this is our 0.1 molar solution. If we took 1 milliliter of this and followed the same process, we could get down to 0.01 molar. We could do it again to get to this solution and get 0.001 molar and then 0.0001 molar for the final solution. This is called a serial dilution. You will be not quite doing this type of dilution, but this is a very common technique to go from a large concentration to a small concentration without wasting a ton of solvent. Okay, now we can observe a trend in these solutions that have been diluted, and that trend is that as we dilute the solution, the color of the solution is decreasing or becoming more transparent, however you want to say it. More clarity, less strong color. This is because there is a stoichiometric relationship between the light-matter interactions and the particles in the solution. And so we're going to leverage that in this lab. And that's where the visible spectroscopy really shines in terms of its utility. Okay, so how does this work? We have a sample, we put it in a cuvette, which is represented by this kind of cubic tube. And so this solution, I'm labeling this solution blue because the solutions we'll be making in lab will be kind of a blue color. We put it into a spectrometer, and the spectrometer shines light of a specific wavelength on the sample. And because the sample is somewhat transparent, hopefully transparent enough that light will come out the other side, otherwise this won't really work, some amount of that light with that specific wavelength will pass through. But not all of it will, because some of it will be absorbed by the particles in the solution. All right, so basically the difference between the light that comes out and the light that was incident or initially shown on the sample will give us some information about how much light was absorbed. So the actual way that we would calculate absorbance from values of incident light and the intensity of the light that came through the other side is here in this formula. We would calculate the absorbance at that specific wavelength, by the log of the initial light intensity divided by the final light intensity. Now, this calculation is done for you automatically in our spectrometer, so we don't really have to worry about this. The spectrometer gives you data in the form of absorbance. And we could shine light at just one wavelength, but if we don't know the properties of the substance that we're working with, we might need to actually first look at how the absorbance relates to wavelength. So we already saw in the previous slide that all of these complexes have different colors. And the reason they have different colors is because they absorb different wavelengths. And so if we scan through one wavelength at a time and look for whichever wavelength will give us the highest amount of absorbance, that will actually tell us what absorbance or what wavelength gives the most sensitive measurements. And so we call that point the value of wavelength with the highest relationship to absorbance, the lambda max for a specific compound. Now, every compound or ion that interacts with light will have a different lambda max associated with it. So it's important to actually measure that before we go into trying to look at the relationship with concentration. Okay, so once we've identified our lambda max, now we can look at how absorbance relates to concentration, because we already said before that obviously the solution that is more clear because it's more dilute has less absorbance of light at a specific wavelength, and that's why its color is not as bright. So if we now know what wavelength is being absorbed most strongly, we can set our spectrometer to that absorbance, and we can create solutions with known concentrations and measure the absorbance of those solutions. And that will help us to understand the relationship between concentration and absorbance at that wavelength for that specific species. So let's imagine we get these data points. All right, so let's say we made 4 solutions. Well, actually, on the previous slide, we had 5 solutions, so I'll just be consistent. Let's say we got these data points for the absorbance for the solutions that we made with our specific concentrations. Remember, we had 1 molar, so let's just pretend that's this one. And then we had 0.0001 as our lowest concentration. So just to kind of frame us back to that. Now, you'll notice that they have a linear trend, and that should be observed in your data in the lab as well, because there is a stoichiometric relationship, and you can get a best fit line, which, sorry, my line is not the straightest here, but you can get the equation for that line in the format of y equals mx plus b. And we'll talk about what the y, m, x, and b of this are. Of course, based on the axes we have here, y should be A and x should be concentration in molarity. But what is the m and what is the b? Well, so this type of plot is known as a Beer's law plot. That's the common term, but the full name is Beer-Lambert law. The Beer-Lambert law is essentially that absorbance is related to concentration as a function of the molar absorptivity of the compound or ion. All right, so this is the formula that you'll use for the Beer-Lambert law. A equals, you might see it various ways. A lot of times I will write it as epsilon BC. Here I have an L, but just know that that could vary. Epsilon is a property of the substance, and it's the molar absorptivity, essentially how many photons are absorbed per mole is sort of conceptually how that works at that wavelength. Then L is the path length, and that's the path of the light through the sample. And this is equal to 1 centimeter pretty much always. So there is usually no need to plug in any value for L. It will just be 1 centimeter. And that's because the cuvette is a centimeter long, or a centimeter wide. C is the concentration, and that should be in molarity, but that means that your molar absorptivity will be in terms of molarity as well, so keep that in mind. And then the last part of the equation is that plus B part, which is, I think this is a delta. It's just the error term. And the error term accounts for the fact that your plot may not go through 0. There may be some y-intercept difference from the origin, and that will account for measurement error, for experimental error, all of that. And so when you later want to measure an unknown concentration, this is where the Beer-Lambert law becomes really important. If you have an unknown concentration and you already went in and, obtained a value for your molar absorptivity, that's really the goal of making a Beer-Lambert plot. You can plug in the measured absorbance, your measured molar absorptivity, your measured error term. People don't always do that part, but that will give you a more accurate value. Your path length is 1 centimeter, so that leaves your ability to calculate the concentration. So that is where this becomes really important. Okay, so when we get to the last part of the experiment, you will be looking at the reaction between a copper metal strip and nitric acid. And the copper metal strip in your solution, so I'm just going to kind of draw it. I'm going to draw the copper in orange because copper's kind of orangish looking. So let's say you had this here, and this is your nitric acid with your copper. You'll see some gas bubbles forming, and that would be your nitrogen dioxide gas. But you'll also see the solution start to turn color. And the color is going to be that kind of bluish color of the copper-2 ions, because copper-2 ions are formed in the reaction. And that will make the absorbance of the solution start to increase, because now the solution is starting to get more and more dissolved copper-2 ions. So as you might imagine, at your different time points, you might see the amount of copper-2 go up, and the shape/steepness of that line will depend on the rate of the reaction. And so that's kind of our research question for this lab, about the rate of the reaction here between the copper metal and the nitric acid. So remember, we're measuring at lambda max at only 1 wavelength, and we're looking at how the absorbance increases over time, because this reaction is taking place and forming something that we can detect by visible spectroscopy. And so you'll use that to reason about the rate of reaction. And we could definitely take each of these points. We know the absorbance. We don't know the concentration. We can calculate what the concentration of copper-2 ions in solution at that time point is using our Beer-Lambert law with our known molar absorptivity. So really kind of what's important is there are 3 types of kind of experimental measurements we can make in visible spectroscopy. There's absorbance versus time. You'll be doing that in the last part of the experiment. There is absorbance versus concentration. You'll be doing this once you've already detected what lambda max is. And there is absorbance versus wavelength, and that is what we use to determine the lambda max. And so you'll start with absorbance versus wavelength, move to absorbance versus concentration, and then at the end of the experiment, look at absorbance versus time. You'll learn how to do this using an app that connects by Bluetooth to the spectrometers, but there are alternatives if that is not going to work appropriately for you. But just go and check the guidelines on how to use whichever technology you select in the Guide to Collecting Digital Data in the Chemistry Lab document.